Hello, everyone. My name is Anthony Armley. I am the Federal Coordinator for the Regional Workforce Initiative here at NETL. I am based out of our Pittsburgh campus. I typically try to start off these Energy 101 webinars with an introduction to what the regional workforce is, for those who aren't familiar with what we do here. So this initiative started in 2017, and we utilized this opportunity to focus on the Appalachian region of the country, where we emphasize the future of advanced manufacturing, energy, workforce readiness, and economic development. And so that's pretty much the gist of what we do with this initiative. So for today, the Energy 101 series, we'll take a technical topic like carbon capture and storage, and we'll present it to an audience that may not necessarily have a technical background. So our goals today are to introduce to you what carbon capture and storage is, why it's important, job implications or opportunities in the future, and skills that may be needed to support those jobs, especially in this region. So the mission, of course, is an extension of what our lab's mission is. And what we're trying to do is get technologies to market from a regional perspective. I mentioned the Appalachian region. That's a big part, and many of you are from that region that are on the call today. One of the things we try to do to promote workforce development at our lab is what we call a technology workforce work plan. So any technologies that we're working on at the lab that are 3 to 5 years from commercialization, our technology managers work with me to put together a list of the skills that would be needed to support that technology in the workforce. We take that workforce work plan and share it with our community colleges in the region, or anyone for that matter that would be interested in that. But we focus on the community colleges, technical schools, so that they can update their curriculum in that 3 to 5 year advanced window. Slide, please. Some things that we do as part of the Regional Workforce Initiative, we put together a Energy 101 series that you're on today, energy workforce webinars, a monthly e-note where we have over 200 plus different people that have subscribed to that. If you are on the call today and you're not part of that distribution list, let me know. You can send me an email. I'll have my contact information at the end here. Or you can go to our website, which I posted in the chat for everybody, netl.doe.gov /business/RWFI. There's an opt-in button. You can just click it, and we'll get you added to that. We post all kinds of, in that monthly email, we put funding opportunity announcements related to energy, advanced manufacturing, workforce development, et cetera, in there. We've had a lot of folks come back and say, wow, thanks for the information. We didn't know about that. We applied, and we were able to get X amount of dollars that we wouldn't otherwise have had. So we feel there's a lot of value to that. We talk about any upcoming events, any newsworthy, noteworthy type of information that's coming out of our lab. It's a way to engage with our region. And so, we really welcome you to subscribe if you're not already. Over the 3+ years that we've been doing this, 3.5 years it is, we've had over 1,000 plus register to our webinar series. We engage with over 350 institutions or organizations. And, we're proud of the engagement and the growth that we've shown in this initiative since we started. 3 things we're trying to do here: coordinate, communicate, and collaborate with our stakeholders in our region. Slide, please. Another item I wanted to bring up about workforce development that we've done, we're very proud of, is last year we teamed up, NETL, Department of Energy, and the Appalachian Regional Commission teamed up for a workforce opportunity where DOE sent $750,000 to ARC. ARC matched with another $250,000. They put out the $1 million funding opportunity announcement, and they selected 5 awardees for advanced welding workforce training. This is an opportunity to prepare a new generation of welders to manufacture and service high-temperature alloy components in electric generating stations. Slide, please. Of the 5 awards, there's a big impact on jobs. The first one, the Robert T. Byrd Institute, which is in Huntington, West Virginia, in their award, which as you can see, it's over $336,000, at least 18 students will obtain new employment. 35 workers or trainees as part of that opportunity with them will be able to obtain new or enhanced career development. The next one in Belmont College in St. Clairsville, Ohio. 50 students they're anticipating will be able to obtain new jobs related to advanced welding or update their current positions. The next one in Calhoun College down in Decatur, Alabama. They said 110 degree-seeking students during the project period will have an opportunity to advance basically their career opportunities because of this. The next one in Cumberland, Kentucky, they're saying in the project that they're proposing that they've been selected for, which serves 3 economically distressed counties, which also include designated opportunity zones, will prepare 15 students in that area for employment with local businesses related to advanced welding. And then the last one, Westmoreland Community College in Youngwood, Pennsylvania. At least 68 students and 21 workers or trainees will obtain new positions or enhance their current employment. We're really proud of this opportunity. I emphasize the jobs here because it aligns with what we're trying to do in the lab and the administration's priorities and really making a difference in these communities. Slide, please. And just going back a little further on that one, if you have an idea of something along those lines where we could team up to do another opportunity like that in this year, next year, whenever, please let me know because we would definitely entertain something like that. We're really excited about the impact that effort with ARC and DOE has made. So just to summarize, I really want to get to the main presentation today with carbon capture and storage. Just the key takeaways with the Regional Workforce Initiative. We're trying to be consistent in our communication and outreach and engaging in our region. We put on these webinars for education and informational purposes. The Energy 101 webinar to explain to the region what NETL does technically, but to a non-technical audience. We have our monthly e-note communication means that we put out each month. I really ask you, if you're not subscribed, to join that list. I think you'll find a lot of value in that. And in the future, please, reach out to us. And if you have an idea of how you can team up with us on any workforce development opportunity, or maybe even team up with us on one of our webinars, we'd be very happy to discuss that with you. Going forward, we're primed for partnerships. NETL is open for business. We welcome that dialogue. Any ideas you have, the conversations is something that we really take enjoyment in, and we're trying to grow this initiative even further than what we already have and try to unlock, positive impact in our region. We think NETL can be the catalyst for that. Next slide, please. A couple things of note that I did want to mention. The new administration is big on jobs. If you haven't heard that already, they're investing in infrastructure and jobs and workforce development. And an instance here is $75 million carbon capture funding opportunity announcement that was recently put out. One of the things that they're talking about now for the first time ever is this funding opportunity announcement is requiring the applicant to consider job impact. That's something historically that those funding opportunities didn't really ask for, but now they are. Job impact, diversity recruitment in underrepresented groups. So just things to think about as you move forward is how can this opportunity affect jobs, workforce, economic development in the region. The next item I want to mention, the Department of Energy Loan Program Office has about $8.5 billion out there for carbon capture and storage opportunities. If you'd like to learn more about that, let me know. I have a really good informative fact sheet that I'd be happy to share with you. But this is something I just want to mention. There's funding out there for efficient technologies such as carbon capture and storage. And then the last item I wanted to mention, if you haven't heard about it before, there was an initial report to the President on empowering workers through revitalizing energy communities. NETL's Director, Brian Anderson, is going to be the lead for this effort. And as part of that report, there's 3 things they're going to be focusing on, if not more. A set of communities across the country that have been hit hard by the coal mine and coal power plant closures. This will be a priority for this administration, focusing on federal investment. Number 2, existing federal programs that are out there with potential availability for funding. They're anticipating that that's somewhere around $40 billion, which could be used to provide immediate investment in these energy communities, especially in Appalachia. And then lastly, the point I wanted to make on this was the immediate steps the interagency working group headed up by NETL's Director Anderson will be making in the next year to support the energy communities. There's a lot of different activities and some different workshops they're going to host for the region to get involved and to take advantage of opportunities that are out there. slide, please. For those that are unfamiliar with NETL, I just want to do a really quick high-level overview of the type of core competencies and technology thrust that we have. We have expertise in computational science and engineering, materials engineering, advanced materials, manufacturing, geological and environmental systems. You'll hear a little bit about that today with the carbon capture and storage, energy conversion engineering, systems engineering and analysis, being able to find where the efficiencies are and put a circle around a box where we could make a big difference in different businesses and especially in the energy sector. And then we have a big program management, program execution and integration group here at the lab. We focus on primarily coal, oil, and gas, but not just those. I mean, we have, under coal, we've got advanced materials, advanced computing. NETL has one of the top 50 supercomputers in the country. Advanced energy systems, water management is an area of emphasis. Rare earth elements, NETL is showing the ability to extract rare earth elements here in the United States. There's a lot of different things that we're working on here that I want you to be aware of. Under the oil and gas program, methane hydrate, offshore programming, where we do studies with oil and gas coming off the Gulf of Mexico. Unconventional oil and gas, infrastructure, which fits along with the administration priorities. So there's a lot of different things other than just coal, oil, and gas that we do here and the technologies that we work on. And so with that gives my quick overview here. Next slide here has my contact information. Please don't hesitate to give me a call, send me an email. I'd be happy to have further discussions with you on how we can work together. And I thank you for your time today. Back to you, Matt.
Thanks, Anthony. So in the interest of time, we're just going to move on to our next presenter.
Okay, so first of all, I would like to thank the organizer for giving me the opportunity to talk at this. I think this is a great forum. And what I would like to do in the next 20 minutes or so, to give you a quick primer on carbon capture technologies that are being developed at the lab as solutions to support the deep decarbonization for both power and industrial sources, as well as negative emission technologies. Also, I'd like to then summarize the mission, structure, and approach of our carbon capture program here at NETL, and present you two case studies on how we scale up transformation and technology and integrate it with the carbon storage program, which Mark Mccoy, my colleague, will talk after me. So, so again, the mission, a little bit on the mission side. The mission is for the program is to develop advanced carbon capture technologies for both industrial and power sectors, as well as negative emission technology to ensure a safe and reliable energy generation. One of the major challenges which we're trying to solve here is that carbon capture has a problem with both capital and operation costs. And what we're trying to do is to reduce this cost over a wide range of feed compositions to support the overall goals to achieve carbon pollution-free electricity sector by 2035 and also zero carbon economy by 2050. To meet these goals, let me just advance this. To meet these goals, our program is developing both carbon reducing and carbon dioxide removal technology, or CDRs, or you'll see in literature called negative emission technologies. I'll go through these cartoons and I'll explain a little bit what we mean by that. So for a typical, in a carbon positive power generation scheme, fossil fuel are used to produce electricity, and then CO2, hopefully you can see my screen, CO2, my pointer here, CO2 is emitted in the atmosphere. Applying carbon capture technologies to this type of processes, a large portion of CO2 is separated and then it's sequestered underground. These are called carbon reducing technology, where you still have a smaller amount of CO2, about 5 to 10% of what has been initially emitted in the atmosphere. Now, in cartoon C, to further reduce the carbon footprint and reach neutrality of this type of operation, the fossil fuel can be mixed with biomass. and the residual CO2 in this situation is balanced by the carbon which is stored in the biomass within the process. So in this way, the process reaches neutrality. Finally, in terms of carbon negative, these are technologies which are pulling out CO2 from the air and then store it underground. So we're working, and the program, as I mentioned, is developing cost-effective technologies which are targeting both carbon capture or carbon-reducing technologies and also CDRs or negative emission technologies. Now, here's some examples. Here's some examples of the type of carbon reducing technologies and also negative emission technologies or CDR. So carbon capture applied for a wide range of sources like power generation in coal plants or natural gas plants, or carbon capture applied to industrial sectors like cement plants, steel plants, hydrogen plants are examples of carbon reducing technologies. One thing to note here is the broad range of concentration of CO2 coming out of these sources. And so the challenge of the program here is to really tune the type of carbon capture technology for a specific flue gas. Now, in terms of the carbon removing technology or CDR, examples are direct air capture, where you're pulling, as I mentioned, CO2 out of the air. The concentration of CO2 in the air is much smaller, 400 ppm, so that could be a challenge to get an effective process. Also, pulling CO2 out of plants producing ethanol. Here, the concentration of CO2 is very high, 90%, or any of the carbon capture technology applied for plants which are utilizing bioenergy, biomass, and these are called BECCS. So, as you can see, a broad range of applications, and the program here at NETL is addressing and again developing technology for most of this, most of these applications. Now, one question which we get very common, very often is this technology, is the carbon capture technology ready for deployment? And the answer is yes. And the two slides I'll show you demonstrate that indeed there are technologies which already been commercialized and they are in operation. The first example is an example for a carbon reducing technology. This is a carbon capture plant which was installed in a hydrogen plant by Air Products. This is located in Port Arthur, Texas. So this plant is operating, currently operating, is capturing about 1 million tons of CO2 per year. As you can see, this is a big chemical plant associated with, again, a hydrogen plant, which is, again, producing hydrogen. Another example I want to give you for the carbon dioxide removal. So this is an area where people are starting to develop commercial offerings. Currently, there are about 15 plants deployed around the globe for a direct air capture. This is here an example of a plant which is currently being constructed in Iceland. This will capture about 4,000 tons of CO2 per year. The energy input for this is provided by a geothermal plant, which is co-located with the direct air capture plant. The other thing which is important to note here is that after CO2 is pulled from the air, CO2 is pumped in the ground, underground, and then where it reacts with minerals to form carbonates and then being stored there. Operation is expected, with construction currently taking place. Operation is expected in late summer 2021 or early next year. So again, these are two examples, and there are many more where these type of technologies are currently being deployed commercially or they're ready for deployment. Now, in the next 2 or 3 slides, what I would like to do is give you a little bit of background on the process description of what carbon capture means, right? So there are two types of processes which we are developing. One, post-combustion and pre-combustion, and that it depends on the location where the carbon capture is integrated in the power generation process. So here is the schematic for post-combustion capture. So applied to in a combustion system. So fossil fuel here is combusted in air to produce heat, which then is used to generate electricity. The flue gas resulted from this process containing CO2, nitrogen, oxygen, and some other small impurities. It's passed to the carbon capture system where CO2 is separated, and then the clean flue gas is released into the atmosphere. And this is called post-combustion because this system is, again, applied to the system after the combustion process. The other process which we're working on is the pre-combustion process. So here, as I mentioned, the carbon capture process is applied before. So the fossil fuel is partially oxidized in actually this time in pure oxygen. Syngas, which is a mixture of hydrogen and CO, are produced, which then is reacted with water to more or less convert most of that CO to CO2. So now the flue gas contains only hydrogen and CO2, which is then passed through this capture system to produce hydrogen, which is used as a fuel and produce electricity, or is used for other purposes, and then CO2, which is again separated and then stored in the ground. So now the program we have is now developing a lot of approaches, or considering a lot of approaches for CO2 capture. One, we're developing solvents which are absorbing CO2, membrane which are separating CO2 from either nitrogen or hydrogen, sorbents which then are absorbing solid materials which are absorbing CO2, and also novel concepts like electrochemical processes or cryogenic processes which will cool down the exhaust to actually separate the CO2. So what I gave you so far, it's kind of a broad overview what carbon capture means, and whether, again, address that question, is it ready? Yes, the answer is ready, but of course there are a lot of challenges, as I mentioned at the beginning, which we still need to solve, primarily around cost and primarily on the diversity of exhaust compositions which we need to deal for different applications. So the next slides will present how the structure and approach of the carbon capture program, which again we have here at NETL. So the carbon capture program we've been working on this for the last 15 years or even more than that. And historically, we developed carbon capture technologies for coal-fired power plants. Back in 2008, and that was culminating with commercializing technologies at a power plant in Texas, which capture CO2 from the 240 megawatts slipstream. At that time, those were first generation technologies, which we work on to lower the CapEx and OpEx and also reduce the regeneration energy, so reduce the energy input for the plant. Now, in 2015, we started promoting the development of we call transformational technologies, which are next generation technologies with better energetics and also better, again, economics. So we include in here water-lean solvents. I'll talk a little bit later about one of these examples, advanced membranes, hybrid systems, and also process identification, which primarily the goal being here is to reduce both CapEx and OpEx through process identification. We are currently scaling up these technologies with real exhaust condition in pilot facility up to like 10 megawatts. The example here, which is shown, is a picture of a pilot facility, actually in Norway. This is Technology Center in Mongstad, one of the biggest plants where we can, or demonstration where we can validate our technologies. Now, this last year, in the last year or so, we expanded our mission and trying to use the portfolio of technologies which we developed in the last 15 years to really, on one end, scale up the transformation technology, and also to develop negative emission technology, as I mentioned, direct air capture and bioenergy with carbon capture, and also reduce emissions for other type of sources like natural gas, and also industrial sources. I mentioned cement plants, steel plants, hydrogen plants. Now, on a more tactical basis, so we developed an integrated approach for rapid technology commercialization. So for us, it's very important that we decrease the time and reduce the risk of this transformation technology to be commercialized. So we developed this integrated approach for rapid technology commercialization for both pre- and post-combustion technology for a wide technology option, as I mentioned, solvents, sorbents, membrane, and novel concepts. The program is actually a joint effort, including national labs, including, of course, our own research here at NETL, academia, small and large businesses, for the best selection of skill sets to achieve our program goals. So recipients in our programs actually test, as I mentioned, novel concepts. These are material or processes in the lab and bench in order to understand how promising these technologies are, and they are doing this with simulated exhaust. Then the most promising ones are starting to be scaled up in small pilots or large pilots. As I mentioned, the largest pilot we have, the one we're testing in Norway, with this time tested technology with real flue gas. We're testing here long-term stability, and also understand what kind of life technologies will have in them with real application. It's very important to understand that in order to evaluate these technologies, we rely a lot on process modeling, techno-economic analysis, and LCA. And NETL has a very skilled and experienced group to perform all these evaluations of the technology which we are developing, to assess whether the technology has merit, and then to very quickly scaling up. The other thing which I want to mention is that we're using this concept, this type of approach for new application like industrial sourcing, direct air capture, or even bioenergy with carbon capture. Also important is that we collaborate very closely with similar European programs such ACT, and also other DOE government agencies such RWFI or Basic Energy Science. So in order to, again, accelerate the technology from the lab into the commercial scale. Now, what I want to show you here is, and again, this is a slide showing the distribution of projects that we're supporting as a function of technology readiness, application space, or type of critical technology. So this is an interactive map. This map will be soon available on our website, and then you get more information on our portfolio. So we have currently over 95 projects, active projects, across all these application spaces. Now, I want to, in the last 3 or 4 slides, what I want to provide you with some information in terms of give you some examples. And one thing which we realized very quickly, like 5 years ago, was the fact that in order to achieve our goals to commercialize technology, we needed to match the technology development for both capture and storage. because at the end of the day, the final product has to capture the CO2 and also store the CO2. So therefore, we developed, and then Mark Mccoy, my colleague coming after me, will describe to you their effort in the storage development and storing carbon. But what we did was we developed two timelines which are integrating together in order by 2025 to have an integrated project, capture and storage together. We have actually called 5 FEED programs, which are matching or fitting this profile. These are regionally integrated between capture programs and also storing CO2. So this is an example of that. So here's an example of a FEED study which is led by Southern Company for a 525 megawatt NGCC plant. So where we apply carbon capture technologies. So the carbon technology is developed by BASF. It's an aqueous amine solvent. And this was actually demonstrated in our program at the pilot scale. So now we are facilitating demonstration of this technology for this NGCC plant. The FEED study will provide a full cost for CCS implementation and will, after that, follow up with hopefully a demonstration project. Note that this project is actually co-located with a carbon storage program, which Mark will talk about it, to characterize and store the site for CO2. So that's the way we're working integration between carbon capture and carbon storage. And my final slide is about a technology, a transformation technology, which we are developing and demonstrating currently at the Technology Center Mongstad. The problem, the challenge we want to solve here is the fact that the current technologies, the Generation 1 technology, are aqueous-based technologies, so they contain about 30% amine and 70% water. Carrying that water has a negative energy impact. So the solution which the RTI, which is the developer here, the Research Triangle Institute came up, is to replace that water in the solvent with a hydrophobic non-aqueous solution. Now, the project started in 2009, went through the technology process of being demonstrated at the lab and bench, scale-up testing in 2016, and now is being validated in this large pilot in Mongstad. The outcome of this would be that we expect reducing CapEx and also OpEx, and which will end up in reducing the overall cost of carbon capture. So this is, again, an example how we carry the technology from lab into the large pilots. Finally, I would like to close my presentation. I wanted to highlight our outreach efforts. If you want to have more information about our program, of course, you can subscribe to our carbon newsletter. This carbon capture newsletter. It's something where you can get information about our recent opportunity announcement, our advances in technology, or other industry news. And also, you can visit our website. There, you also can find the Carbon Capture Program R&D Compendium, which is a great selection of technology we've been working on. So it could give you a good sense of if you have one details about one of the technology which we have selected. So with that, I would like to thank you for your attention, and I will entertain any question you might have at the end of the hour. Thank you very much.
Okay, if this will work, let me get started. So I'm Mark Mccoy. I'm the Technology Manager for Carbon Storage here at NETL. And the presentation I have is with regard to the DOE's Carbon Storage Program. And one thing that I do want to make clear is that when we talk about DOE's Carbon Storage Program, the one that I manage, it does not include the storage of carbon within the ocean seafloor or storage of carbon within soils or within biomass of forest. We're referring to injection of CO2 underground, such as through a well, as shown on this particular photograph on the first slide. There are, one question is, why do we need to do carbon storage? And of course, the situation is one whereby the concentration of CO2 in the atmosphere has been going up, as indicated by this line here. Globally, the emissions are now over 30 billion tons per year. Even if all of the stated policies by the different governments are implemented, that would simply level out the carbon emissions at around 35 billion tons per year globally. And most scientists who are studying this indicate that we really need to drive the emissions down to a net zero situation as soon as we can. A number of modeling studies have been done looking at the various mixes of things that can be done to drive this down. Those, of course, include improvements in energy efficiency, switching from fossil fuels to renewables, and other things that can be done. But almost all of the scenarios indicate that at least some amount of carbon capture and storage will be necessary to achieve a net zero emissions. So given that, I'll launch further into describing, well, what do we do, what do we mean when we talk about geologic storage of carbon? So what we're going to do is look in the deep subsurface for a rock layer, a rock stratum, that would have sufficient permeability and porosity to allow us to inject the CO2 and to store it within the pore spaces. So if you're sitting on a beach and you have a cup of water and you pour that water onto the sand, that water will almost instantly go right down into the sand because the sand is very permeable. The water will go into the pore spaces between the mineral grains of the sand. So in the deep subsurface, we're going to look for a rock that is very similar to those beach sands. In fact, the rock might be a sandstone that may be derived from an ancient beach. And as long as that rock unit still has sufficient permeability and porosity, then we can consider using it. It also must have a sufficient lateral extent such that we can inject CO2 and the pressures don't build up too quickly. Now, to keep the CO2 in place, because CO2 would be buoyant relative to any other fluids in the subsurface, that rock layer will need to have an impermeable rock layer above, which we refer to as a cap rock layer or a seal rock layer. So how is it we're going to store enough CO2? A lot of people think, well, why don't you just find, caverns or large voids underground, maybe salt solution caverns or limestone caverns deep underground, and inject the CO2 into that. But the volume of space there would be just trivial in comparison to the amount of space that's needed to store the CO2. Using the porous and permeable rock, actually in total, there's more pore space that we can use, but we need to be able to compress the CO2 into a very dense phase such that when we utilize that pore space, we can use it very efficiently. So in this little illustration over on the left, what you see there is a balloon. Let's say it has 100 liters of carbon dioxide in the balloon at the ground surface. As you pump that CO2 underground deeper and deeper, due to basically the hydrostatic pressures from the water table down, that CO2 is going to be compressed more and more by the hydrostatic pressure. So as you go deeper, it gets smaller and smaller. Once you get below about 800 meters or 2,600 feet, that CO2 will be compressed into what we call the dense phase. At that point, it'll have less than 1% of the volume that it has at the land surface. And when we say a dense phase, if you were to see that CO2 flowing through a clear pipe, it would look like a liquid. But if you opened the pipe, the CO2 would readily expand like a gas. So it's in what we call the supercritical state. It's between being a true liquid and a true gas. But that allows us to inject that supercritical CO2 in a dense phase and make good use of the very small pore spaces that exist in the deep subsurface. So when we're storing the CO2 in the subsurface, we really want to get well below that threshold for supercritical state with the CO2. So we'd like to be at 3,000 feet or deeper, maybe 5,000, 10,000 foot depth. In the sedimentary rock, we want to find a nice, permeable, porous stratum in which to inject CO2, where that stratum is laterally continuous so the pressures don't build up, a laterally continuous cap rock or seal layer above, and then we want thousands of feet of sedimentary rock between that main cap rock and any groundwater aquifers, where we would have interlayered permeable layers and impermeable layers, such that if any leakage occurred through the fractures in that cap rock, the CO2 would simply go into the next permeable layer and start to spread there, because there's another cap rock above that. And if that one leaked, then it would go to the next permeable layer above. So with thousands of feet of interlayered porous and permeable layers and impermeable layers, there's very little chance of leakage through the rock all the way up to the groundwater aquifers. Now, we still have to choose the sites very carefully. So we want to look for sites where there are not leaky old wells. So we have to find the old wells. We have to assess the integrity of those wells. If we are worried that they could present a leak problem, we may have to fill them full of cement to plug them. We also have to look for faults that might cut through the cap rock layer and extend a significant distance upwards. And if there are faults, we have to assess those for whether they are transmissive faults to liquids, whether liquids could move up them, or whether they are sealing faults and would serve as barriers that help keep the CO2 maybe where we want it to be. So not all faults are going to be leaky. We have to assess the faults. The same with fracture zones. But selecting the site is really an important step in the process of securely keeping the CO2 underground for a long period of time. Now, early in our program, we had some partnerships that were established to look at the resources in different regions of the lower 48 and the western provinces of Canada. They looked in the sedimentary basins for sedimentary rock layers more than about 3,000 foot depth with sufficient porosity and permeability and a nice cap rock above, and they assessed the volumetric storage capacity. That would be sort of the ideal or the storage potential that might exist within those rock layers. And just looking at the onshore, what they found was, for example, with oil and natural gas reservoirs that are depleted, well, there you know it has good integrity with the cap rock because it's held oil and gas for a long time. You can assume that you can inject a volume of CO2 equivalent to the oil and gas and water that has been pumped out over time with a lot of assurance. So they found in the range of around 200 billion metric tons of CO2 could be stored there. In unminable coal seams, somewhat less. In what we call saline formations, 1 to 2 orders of magnitude more storage capacity may exist. But when we say saline formations, what we're referring to are those porous and permeable formations that are filled with brine, which is a relatively incompressible fluid. So even though we might be able to use only a small percentage of that pore space, even if only 5% was usable, we still have a very significant amount of storage capacity compared to the emissions that we have to worry about in the United States. So if you think about our emissions of CO2 from fossil fuels, we're emitting in the United States between 5 and 6 billion tons of CO2 each year. By the time we do further improvements in energy efficiency, substitute renewables, and other things that can be done, we might still need to be able to capture and store 1 billion tons per year, maybe 2. And so with that kind of rate, we would be able to store the emissions that occur, with those emissions occurring over decades. So there is enough storage capacity in existence in the deep subsurface for storing the CO2. So what is the role that the Department of Energy plays with regard to CCUS? I want to make it clear that we are not a regulatory organization. We do not write regulations. We don't enforce regulations. For the most part, we are not a policy-making organization. That is something that state legislatures, Congress, local governments do. what we do is we sponsor research and development of the technologies that enable the specific things that benefit our society with regard to energy, and in this case with regard to carbon capture and storage. So while the funding is provided through Congress, and Congress may provide some specific directions, we have to apply that funding in the achievement of the goals and objectives of the carbon storage program. Now, our historical focus has been on developing and demonstrating tools and techniques for safe and long-term storage, but now we're starting to put a lot more focus on enabling the launch of a carbon storage industry. And it's going to take an industry to be able to store the amounts of CO2 that we want to store. We want to be able to reduce the project cost, because obviously we want for this to be affordable for our society. And we want to reduce the risk as we deploy this widely. There are more opportunities for things to go wrong, so we want to make sure we mitigate those risks as much as practical. And to be able to show others how this can be done, we want to support the early demonstration projects. Now, to speak a little further to the program objectives, primarily we do focus on developing the technologies. We may do that with laboratory experiments or computational methods, or doing field work whereby we do measurements in the field or tests or experiments in the field. We also support doing demonstration projects, and mostly those have been in the way of pilot scale projects or first-of-a-kind projects to reduce the risk for those who are the first movers. But increasingly, we may be pushing for a little bit beyond that to have more projects demonstrating in different geologic regions and in different settings that carbon storage can be done safely and effectively. Now, some of the research that we do is within the laboratories of the Department of Energy, both the NETL and the other national labs. I've shown here some of the projects that are in progress just by name, just as some examples of some of the things we sponsor: development of different types of sensors that can detect corrosion in casing or the failure of the cements within wells, developing tools and methods for assessing the risk of leaks and induced seismicity, doing studies on the interactions of CO2 and brine with wellbore cements, looking at various geochemical parameters that could be signals of leakage. So we have worked on a wide variety of technologies to enable geologic carbon storage. But not all of that research is done within the DOE laboratories. We actually fund quite a bit of research at universities, within industry itself, at other laboratories, to cover a wide spectrum of things. And these are just a few examples here, such as being able to remediate failures in the cement around the casing within a well, or developing geophysical techniques to be able to map where the CO2 has traveled to as it's being injected into the deep subsurface, using, for example, advanced electromagnetics or newer approaches to seismic data acquisition and analysis. We also further the development of computational tools, such as reservoir simulators, that would help us predict where CO2 will go once it's. With regard to the larger scale field projects, this is just a listing of the different initiatives, and I don't want to spend much time on that here, but I do want to point out that among our projects we have injected more than 11 million metric tons within the carbon storage program itself, and within, if you include the major demonstrations that NETL has sponsored, a total of 21 million metric tons. That's a drop in the bucket, but we're paving the way for others who will do this commercially in the future. So speaking of commercial projects for storage of CO2, our flagship initiative is the Carbon Safe Initiative. And the orange text on this map here shows 5 different sites and 5 different projects that we have ongoing at the moment, where they are in the midst of what we call phase 3. They are assessing or doing the detailed characterization of their sites. They are preparing their permit applications, and they will be submitting those permit applications, and hopefully at the end of the projects they will have in hand their permits to construct the facilities. Now, fortunately, the locations of these happen to also be near other sites where the Department of Energy is funding engineering studies regarding the capture of CO2. So what we hope to have are a pairing, a matching of the point sources where the CO2 will be captured with the storage sites, and hopefully we'll have transport of the CO2 established between the two locations such that we have the full system for capture and storage of CO2. When I say commercial scale facilities, these are facilities that would hold at least 50 million metric tons of CO2, with that CO2 being injected over a time period of 30 years or less. So the injection rates would be in terms of more than 1 million tons of CO2 per year. Just as an example, for one of these carbon-safe projects, the one in Kemper County, Mississippi, this one is located on the Gulf Coastal Plain sediment, where sediments are they're not so brittle, so they don't have so much fracturing that would be leaky. The sandstone layers still have a lot of porosity and permeability, which should make for world-class facilities for storage of CO2. At that particular site, they're hoping to receive CO2 from 3 different power plants. And if that happens, they would be able to inject up to 22.5 million metric tons of CO2 each year. That'll be a 4x increase relative to the largest storage project that exists today. And within their 30,000 acres of property holdings where they can inject the CO2, they could inject, in theory, up to nearly 1 billion CO2. Now, again, we've worked with partnerships over the years. The former 7 regional partnerships have now been reduced down to 4 regional partnerships. These partnerships they're no longer injecting CO2 themselves, but what they will do is they will assist others who would inject CO2. So in terms of providing others technical information, business contacts, lessons learned, things that will enable others to be able to undertake commercial scale carbon storage projects, the regional initiatives should be providing that kind of assistance. They also will continue to collect and assess information, making that available to regulators, policymakers, scientists, and engineers alike. I realize I'm short on time, so I'm going to go a little faster here with regard to the offshore. We've hired others to do assessments in the offshore. There are just some graphics showing some examples, but the outcome is in the offshore we're finding that there are hundreds of gigatons of storage potential. Doesn't mean that all of that can be used, but even if a small percentage can be used, we can store all of the CO2 we need to store for a long period of time. We've sponsored other projects regarding storage of CO2 in association with enhanced oil recovery from different settings. We've sponsored other projects where we study how we can better manage pressure buildup on the projects. And just to get to my last slide here, there have been at least a few studies, not really our own work, but a few other studies that have looked at the number of jobs that might be created. And this particular study was sponsored by the Great Plains Institute. They've done a great job looking at this issue. But in terms of jobs created across the carbon capture retrofits that may occur with just existing industrial facilities and power plants, CO2 transport and CO2 infrastructure, just looking at this mid-continent region that's shaded here in darker color, they are predicting for direct jobs, tens of thousands of jobs would be created in association with this. These are jobs that relate to the planning, the design, the construction, and then subsequently the operations of these facilities. And So if you added in equivalent numbers of jobs along the East Coast and the West Coast, again, you'd see comparable numbers of additional jobs being added to these listings. So we're talking about potentially tens of thousands of jobs for engineers, people with technical skills of a wide variety of types who could help with the planning, design, construction, and operation of these facilities. So that's it.
Thank you very much. I think this is demonstrated in the fact that the carbon capture and utilization and storage is a very complex technology with a lot of different facets to it. I think both presenters showcased that NETL, again, is one of the leaders in this technology, and there is just literally a number of different facets to it and a number of different challenges that are being worked on currently. We're a little bit over time. For those that need to leave, this is being recorded, and we will also have slides available. But I did want to take a little bit of time to talk a little bit about, as an overview, some of the stuff you guys had presented today. We did get a couple of questions. A lot of them, some of them were technical, and what we will do with the technical questions, and we've been asked, we're more than happy to link you up with Dan or Mark through our email address. But you ended the discussion with a little bit of talk about the workforce and economic development implications. We did have one question about the carbon capture part of this. Is there any difference in the economics between pre-combustion and post-combustion technology, Dan? Is one more expensive than the other, or one more like CapEx intensive?
So in terms of the cost of the capture unit itself, those are comparable. The only problem or the only technological issue you have is the fact that plants which are implemented on pre-combustion, they will require, first of all, pure oxygen, and also you can have gasification. So depending on the unit, so the process of gasification, it's not as scale up as the combustion process. So that's one of the major challenges. But from the point of view of the capture units themselves, they are similar in terms of in terms of the cost. They are utilizing different types of solvents and system, because you have to separate CO2 from hydrogen or CO2 from nitrogen. So it's a different system. But that would be the major difference between the two.
Mark, these are pretty aggressive goals about the widespread utilization of carbon capture and utilization and storage technologies in the next, like by 2035 and close to those. What do you see as being the main challenges and main drivers to facilitating that goal?
Well, of course, a lot of people point to the fact that with regard to carbon capture and storage, most of the costs at the moment are on the capture side. The storage is much less costly than the capture. So we need to be able to get those costs down, and that's what the carbon capture program is working on. Beyond that, almost everybody points to the financial incentives for this to happen. And so 45Q has triggered a lot of interest. The questions will be, will there be further incentives that will accelerate the shift in this direction? So I guess, I'll be interested to see what happens, like everybody else will.
So I think one of the other promises, I guess, from the administration standpoint is that a number of these jobs that are in carbon capture, utilization, and storage are very translational to what's already currently a job, right? So there's not perhaps maybe much upskilling that could be occurring that needs to be done. What have you guys ever thought about what the workforce skills are necessary for the utilization of your technologies? I would think like at least in the storage part, there's a ready, willing workforce for that. But I don't know about the carbon capture side. Perhaps in the professional area, or professional occupations, there probably is a lot more training that needs to be done because these are new technologies. But have either of you thought about the workforce necessary for the implementation and commercialization of your technologies?
Well, I'll speak first with regard to storage and maybe pipelines too. With regard to storage, I think people who are working right now in the oil and gas industry, they have the right skill set, the right knowledge. Reservoir engineers they're people who are specifically trained with the subsurface, along with a lot of geologists, and it's essentially the very same sets of skills and knowledge that will be used for storage of CO2. So, I think we have the workforce that exists. We have even the business structures and business contacts there to enable this to happen. We're just doing something a little bit different than what was done before, but it's very similar. With regard to pipelines, again, the people who build pipelines today for transport of natural gas and other things, those same skills would be deployable for pipelines to transport CO2. So I'll let Dan speak to the capture side.
I think on the capture side, as you probably saw in the pictures I showed during my presentation, the capture plants are chemical plants, right? So the workforce which you normally would have on a chemical plant will be definitely trained to run those type of carbon capture plants. So chemical engineer, mechanical engineers, those will be chemists. Those will be the type of workforce which you think which will have that will be needed to run those plants. And of course, a lot of during the construction stage, those are all the construction skills which are needed, of course, for that stage of the process. But plant itself, it's primarily chemical, mechanical engineers, chemists, which will be definitely needed for those plants.
And then something out of left field. What do you guys feel? Is there a potential upswing or around innovation and entrepreneurship around carbon capture and storage? Or is there space for that? Because that is a very potent driver of workforce and economic development for regions, particularly the Appalachian region, which a number of the technologies you're working on are probably going to be directly implemented. So what are your thoughts about what space there is for innovations in your technologies that you're doing right now for entrepreneurs to step up and do stuff to solve problems?
Within storage, as we develop new technologies, there will be those who commercialize those technologies. And in some instances, these will be existing businesses, both large businesses and small businesses, but in other instances, there will be new startups. There are just some new technologies that are being developed, and there would be opportunities for individuals to launch their own enterprise. So I think that is going to happen. Now, with regard to storage in general, there will be a lot of opportunities for folks to maybe launch businesses in this space, but it is rather technical. There's a lot of regulation that's involved that would require whoever's working in this area, depending on what they're doing, if it touches upon the regulated space, they're going to have to learn what they have to comply with. So there'll be a lot of things like that have to be dealt with, but certainly savvy individuals would be able to start up businesses. What we're seeing today, I think, is a lot of existing businesses wanting to transition over to this new lower carbon economy, doing things like carbon capture, transport, and storage. So I see a lot of movement among the existing businesses today.
I just wanted to end on that note. I think we have a plethora of questions that came in, which is great. And I wish we had time to get to every question that we got in. It just shows that this is the registration was near capacity, and we're getting a lot of questions, a lot of feedback. This is going to be a very important technology that NETL is developing, and we may need to do another one of these 101s just to keep the conversation going. I want to thank you guys for presenting in very well, like some background terms, and for people like me that are still trying to figure out the technologies. I understood it, so that's great. Anthony, do you have anything to close off on besides making sure people connect with us?
Yeah, just I want to emphasize that again. You know, we have Dan and Mark, both of their email addresses, and I gave everyone my email address. Please don't hesitate to reach out. If you have any further questions about any of this, these technical type topics, please, we'd be happy to continue the conversation. And then I also just wanted to put another plug in. Visit our website. I linked it here in the chat at the very beginning. And, you know, if you're not subscribed to our email, please do. We have another Energy 101 we're planning for next month. The topic will be related to the science-based artificial intelligence machine learning efforts that NETL is ramping up. And I think you'll really be interested in that one as well. So thanks again for everyone for your time today. We did go a little over. I apologize for that, but really interesting topics. Have a great day.
Thanks, everybody. And thank you, presenters, for presenting in your time. Thanks, everybody.
Thank you.
Thank
Till next
you.
time.